One of the first things that you have to do with the Rheometer is calibrate it. And so I'm going to show you how the process has been simplified with this version. The first thing that you'll need is the calibration sheet that came with the sensor, the torque sensor. You'll also need the resistor that's provided. There's a spot on the controller board to solder the resistor. Once you have the resistor in place, you need to grab two values off the calibration sheet. The equivalent shunt calibration and the output at 600 pound-inches of force for the counterclockwise data. Alright, once you have that, we can move to the second sheet. Alright, again, this is the information that's coming from the calibration sheet. We know that we're using data that's for 600 pounds of force. We have the sensitivity at full scale, and we have the amount of force that the resistor represents. Now, from our knowledge of the circuit design, we gather that we get this 4 volts, which is the power we're sourcing to the sensor. We know the op-amp amplification. We're doing a 300x with a differential op-amp. And then the analog to digital converter has an additional 2x of gain for a total of 600 times the signal. Alright, now this rather long equation, which is pretty simple, just multiplication, is the sensitivity times the power that we're sourcing times the op-amp gain times the force represented by the resistor divided by the 600 full scale force gives us the output we expect to see from our resistor, 965.62 millivolts. We take this value, we convert it to volts, which means divide it by 1,000, and we stick it into this equation down here. This will give us the output from the analog to digital converter. This is a 24-bit analog to digital converter. We are centering the signal at half scale. Since it's 24-bit, half scale is 2 to the 23rd. Then we multiply it times the output, the anticipated output of the resistor, times 2, divided by the amount of power we're sourcing to the sensor, plus 1, gives us this magic number. 12,438,711. So there's a software tool that will put this and this value into our Rheometer, and it's calibrated. Now we want to talk about the software. We've got a lot of the software in place already, but it's where most of the remaining work is. You can see the main user interface here. On the left-hand side, we have the stress growth test. On the right side, we've got the flow curve test. At the bottom is a status bar that has some useful information. If you look at the leftmost cell, that contains just general information. Right now we're not running a test or anything, so it's just showing you the unique serial number of your Rheometer. The second cell is giving us the firmware version from the controller board. As soon as communications are established between the software and the controller board, it will get the firmware version and calibrate. The next cell has the calibration information and the motor state. The calibration information is very interesting because I took the numbers that we calculated earlier and I put them onto the system, and when the system powered up, the controller switched in the calibration resistor, acquired a reading, and compared it to the expectation we gave it based on our calculations from the calibration sheet. And they agreed within 0.1%, which is awesome. And the final cell is the software version, the user interface. So now we're going to go ahead and run the flow curve test. Alright, before we start it though, take a look at the controller board. You'll see one LED flashing every half second. That is the heartbeat indicator. That basically means that the USB is sourcing power to the micro, and the micro is running code. There's another LED that if you're careful and observant, you'll see it flashes about every 5 seconds. And that is an indication that the software is talking to the controller board. That's where it's gathering that motor state, calibration, and serial number information. Alright, so our flow curve test is going to have a breakdown time of 10 seconds, a breakdown speed of 30 RPM. It's going to capture 7 points. It's going to stay on each point for 5 seconds. The first point is going to be taken at 30 RPM and the last at 3. Alright, so here we go. Alright, so we expect to stay at this basic level until we get 15 seconds into the test. That's the 10-second breakdown plus the first 5 seconds for the first step. There we go, right at 15 seconds. And now at 20. Now, one thing to note here is that even though the axes are labeled torque and speed, what you're actually seeing is torque over time. One of the tasks remaining to be done is to translate this into your typical flow curve graph. But we got some very nice data here. It's interesting to see as the steps down that the torque undershoots and then comes back up and stabilizes. You can see some periodic nature in the mixing. I believe it's the interface between the fins and the ribs you put in the vessel. Alright, now let's go take a look at the stress growth test. Now, the stress growth test, at least with this fluid, only takes a moment. I'll go ahead and let it run for 5 seconds. And then we'll zoom in and look at it. Okay, we've got our 5 seconds worth of data. Now if you click and drag from the top left to the bottom right, you basically are telling the system to zoom in. And then you right click and drag, and we can position this window where we want it. At the moment, these are in imperial units, so these are foot inches, or pound inches, not Newton meters. But we can see we had a peak torque at just over 4 at about 4/10 of a second. So there you go. That is the software and data collection.